From space, Earth does not look like a scientific argument. It looks complete. Blue oceans wrap around continents. White clouds move through an atmosphere that carries heat and water across the globe. Beneath them, rock, air, sunlight, and chemistry have remained connected long enough for life to transform the planet itself. Of every world humanity has examined, Earth is the only one known to possess this entire chain. It is not merely located where life might survive, it is inhabited. Now imagine opening an atlas of the galaxy and searching for another page like this one. During most of human history, that atlas contained only the planets orbiting our Sun. Then, within a few decades, the number of confirmed planets beyond the solar system rose from 0 to more than 6,000. They circle red dwarfs, stars like the Sun, stellar remnants, and systems containing several worlds packed into orbits smaller than Mercury's. The discovery appears to answer an ancient question with overwhelming abundance. Planets are not rare exceptions. They are everywhere. But a planet is not automatically a place where life could live. Most known exoplanets are giants, scorched worlds, frozen bodies, or planets whose basic nature remains uncertain. Even among worlds moving through a star's habitable zone, the region where surface water could remain liquid under suitable conditions, many are too large to be rocky. Others receive the right amount of energy, but may have no atmosphere to hold heat, no water to circulate, or no stable surface at all. This is where the apparent map begins to dissolve. A published 2026 analysis began with the known exoplanet census and identified 290 planets inside an empirical habitable zone, a broad boundary informed by the histories of Venus and Mars. When researchers applied limits intended to select rocky worlds, the number fell to 45. When they used a narrower zone based on three-dimensional climate modeling, only 24 remained. These numbers do not describe 45 discovered Earths, or even 45 worlds known to have oceans. They describe targets that have passed the earliest tests in a much longer investigation. We can think of each target as carrying an unfinished passport. The first stamp records an orbit receiving a potentially suitable amount of stellar energy. Another asks whether the planet is truly rocky. Further pages wait for evidence of an atmosphere, a stable climate, liquid water, useful chemistry, and an energy source life could exploit. Earth possesses every stamp because we can examine it directly. For almost every exoplanet, most pages remain blank. Even the number of passports changes. New planets are confirmed. Stellar measurements improve. Estimated radii and masses are revised. A world can enter a habitable zone catalog because updated data move its orbit across a model boundary, then leave when uncertainty narrows. Different catalogs can produce different totals because they use different definitions of the zone and different limits for what counts as rocky. There is no permanent list called every potentially habitable planet. So this journey requires a more honest kind of map. It must be dated. Its borders must be explained. Every destination must be labeled according to what has been measured, what has been inferred, and what remains unknown. The 45 rocky candidates in the published 2026 catalog will form its distant route. Earth, Venus, Mars, and the ocean worlds of our solar system will provide the examples needed to read it. The goal is not to imagine beaches beneath unfamiliar suns. It is to follow the evidence as each world approaches or fails the next test. Some candidates will appear promising because they resemble Earth in size. Others matter because they orbit nearby stars and may eventually be photographed. A few allow astronomers to examine the inner or outer limits of possible surface water. Their importance lies not in what illustrations show, but in what observations can prove. At the beginning of our journey, then, the galaxy offers no finished collection of living Earths. It offers thousands of detected planets, dozens of carefully selected possibilities, and one confirmed example. The map cannot yet show where life can live, but it can show where the most precise questions should be asked. That distinction will guide every stop, because the distance between possibility and proof is the real territory we must cross, far wider than the light years separating one candidate from another in the dark still ahead. And with each unanswered page in each planetary passport, the first question becomes unavoidable. What does potentially habitable actually mean? Potentially habitable sounds like a description of a planet. In practice, it is a description of what scientists have not yet ruled out. The phrase does not mean that a world has oceans, breathable air, comfortable temperatures, or life. It means that the limited measurements available remain consistent with some conditions under which liquid water could exist. That distinction is the first rule for reading our unfinished atlas. Every world begins at the lowest level of certainty: detection. Astronomers must show that a planet is really present, usually by measuring the shadow it creates while crossing its star, or the small gravitational pull it exerts on that star. From those signals, they can determine an orbit and estimate a size, a mass, or sometimes both. These are measured properties, although every measurement carries uncertainty. The next level is interpretation. A planet with a small enough radius or mass may be classified as probably rocky. Yet probably is essential. A radius does not reveal a surface. Two planets of similar size can contain different proportions of iron, rock, water, gas, or ice. When both mass and radius are known, researchers can calculate average density and reduce the possibilities, but they still cannot reconstruct every layer inside the world. Then comes the habitable zone. This is the range of orbital distances where a rocky planet with suitable atmospheric conditions could maintain liquid water on its surface. The zone is calculated from the energy produced by the star, the kind of light it emits, and models of how a planetary atmosphere responds. It is not a region where telescopes have detected oceans. It is a region where an ocean is not immediately forbidden by the expected climate. That conditional wording changes everything. Place the Moon in the Sun's habitable zone, and it does not acquire seas or air. It already travels through that zone beside Earth, yet its surface experiences extreme temperatures because it lacks a substantial atmosphere. A suitable orbit can provide energy, but it cannot manufacture the planetary system needed to manage that energy. There is also no single border accepted for every purpose. A conservative habitable zone uses stricter climate limits. Its inner edge is associated with water loss and greenhouse warming. Its outer edge, with the point where additional carbon dioxide can no longer provide enough warming. An empirical zone extends farther by using ancient evidence that Venus may once have had water, and that early Mars supported rivers and lakes. A three-dimensional climate model may shift a boundary again by including clouds, circulation, rotation, and regional differences. These approaches produce different lists because they ask related but different questions. A broad empirical zone is useful for testing where surface habitability might fail. A narrower model zone selects worlds that satisfy more restrictive assumptions. Neither list confirms an environment. Both organize targets for observation. For this journey, the published 2026 catalog supplies a clear rule. It selected planets in an empirical habitable zone and then applied limits intended to retain likely rocky bodies. Transiting planets could be no larger than twice Earth's radius. Non-transiting planets, for which radius may be unknown, could be no more massive than 5 Earths. Under those rules, 45 worlds formed the primary catalog. 24 also occupied the narrower zone used in the analysis. 9 additional planets deserve a separate label. Their central measurements did not place them securely inside the empirical zone, but the full range of their uncertainties overlapped it. Improved observations could move some into the catalog or exclude them. Calling these worlds provisional is not indecision. It records exactly what the data permit. This gives our atlas several kinds of passport. A nominal candidate meets the selected criteria using its reported central values. A narrower zone candidate passes a stricter orbital climate filter. An uncertainty overlap world waits for better measurements. Some planets are also marked controversial because their existence or parameters require additional confirmation. These categories must remain visible throughout the journey. Combining them into one impressive total would erase the scientific meaning of the map. Even a secure place among the 45 supplies only the first stamps. A planet may receive roughly the right amount of starlight and appear small enough to be rocky, while its atmosphere remains completely unknown. Without atmospheric pressure, surface water could evaporate, freeze, or escape. With too much greenhouse gas, the surface could become hotter than the orbit alone suggests. Clouds might cool one world and warm another. A star's violent youth might strip away water before the planet reaches the conditions we observe today. This is why potentially habitable and habitable are not neighboring words on a simple scale. The first is a search category. The second is an environmental conclusion, requiring evidence that astronomers rarely possess for distant rocky planets. Inhabited is a further claim, requiring evidence of life, and no observation has established that for any world beyond Earth. Our journey will therefore use a fixed hierarchy. We will begin with observed facts: orbit, period, radius, mass, stellar type, and measured radiation. We will then identify inferences, such as likely rockiness. Climate models will be presented as conditional outcomes, not photographs. Atmospheric measurements will be described according to what they detect or rule out. Unknown conditions will remain unknown, even when an artist's image supplies mountains, clouds, or blue water. This discipline makes the planets more interesting, because each tests a different limit. Inner edge worlds probe greenhouse warming. Outer edge worlds test how far atmospheres can extend warmth. Nearby planets may eventually be photographed, while transiting planets may reveal atmospheric signals. Different candidates answer different parts of the question. The preliminary answer to our title is now clear. There are dozens of known planets that satisfy defensible first-stage criteria for potential surface habitability. There are not dozens of confirmed Earths. The catalog is a list of places where evidence should be sought, not a list of environments already found. To understand why those first-stage criteria have value at all, we must return to the only planetary system whose worlds can be examined closely. Here, the same sun illuminates a furnace, a living ocean planet, and a frozen desert. Venus, Earth, and Mars show what an orbital zone can predict, what it cannot, and why every distant candidate must carry more than a single stamp. Before looking across interstellar distances, we can test the idea of habitability within our own planetary neighborhood. Venus, Earth, and Mars formed around the same star from broadly similar raw materials. All three are rocky. All three have atmospheres, although the atmosphere of Mars is now extremely thin. Their locations span the region that inspired many habitable zone boundaries. Yet their present surfaces offer three radically different outcomes: a furnace, a living ocean world, and a frozen desert. The contrast begins with stellar energy. Every planet intercepts radiation from the Sun. The closer the planet orbits, the more energy reaches each unit of its surface. Some of that light is reflected back into space by clouds, ice, dust, or bright ground. The rest is absorbed and later released as infrared heat. If the planet had no atmosphere, this balance between incoming and outgoing energy would provide a useful first estimate of temperature. But a surface does not experience that simplified temperature alone. Atmospheric gases absorb part of the outgoing infrared energy and return some of it downward. This natural greenhouse effect keeps Earth far warmer than it would otherwise be. Without it, much of our planet's water would freeze. The greenhouse effect is therefore not an environmental failure. It is one of the systems that makes Earth's surface habitable. Problems emerge when feedback drives that warming beyond a stable range. Venus receives more sunlight than Earth and reflects a large fraction of it through brilliant clouds. From a distance, that brightness might suggest a relatively cool planet. Beneath the clouds, however, lies an atmosphere dominated by carbon dioxide, with surface pressure crushing compared with Earth's, and temperatures hot enough to melt lead. The atmosphere traps heat so effectively that the surface is hotter than Mercury's, even though Mercury orbits closer to the Sun. Venus shows why a planet cannot be judged from orbit alone. Its present climate is associated with a powerful greenhouse state, but its history matters as much as its current position. Evidence and models suggest that Venus lost enormous quantities of water over time. As water reached the upper atmosphere, sunlight broke its molecules apart. Light hydrogen escaped into space. With less surface water available to participate in climate regulation, the planet moved farther from the conditions familiar on Earth. The exact pathway remains an active subject of research. Scientists continue to investigate when Venus became so hot, whether it once maintained oceans, and how quickly its climate changed. The responsible conclusion is not that every inner-edge planet becomes Venus. It is that increasing stellar energy can trigger water loss and greenhouse feedback under some planetary conditions. Venus marks a warning boundary, not a universal timetable. Earth occupies the middle orbit, but distance alone did not guarantee its result. Our planet carries abundant surface water, an atmosphere thick enough to redistribute heat, and greenhouse gases in concentrations that support liquid oceans rather than destroy them. Clouds reflect sunlight and trap infrared energy. Ice brightens the surface and can amplify cooling. Oceans store heat and move it between regions. Rock, water, air, and life exchange carbon across timescales extending from seasons to millions of years. These connections make climate a system rather than a thermostat. When carbon dioxide dissolves in rainwater and reacts with exposed rock, some carbon eventually becomes locked in sediments. Volcanic and geological activity return carbon to the atmosphere. This long exchange can influence climate stability, although its operation has varied throughout Earth's history, should not be treated as a perfect automatic regulator. Earth has experienced ice ages, extreme warmth, impacts, mass extinctions, and major atmospheric transformations. Habitability has survived change. It has never meant permanent comfort everywhere. Earth's passport is complete because we can inspect the evidence directly. Liquid water covers much of the surface. The atmosphere is measured. Energy enters from sunlight and from chemical reactions. Essential elements circulate through oceans, rocks, air, and organisms. Most decisively, life is present. Yet even this confirmed habitable world warns against using a single frozen image. Early Earth did not possess today's atmosphere, continents, or ecosystems. A planet can remain habitable while changing almost beyond recognition. Mars provides the third outcome. It orbits farther from the Sun and receives less energy. Today, its atmosphere is less than 1% of Earth's surface pressure. Its average conditions are cold, and stable liquid water cannot persist across most of the exposed surface. Water ice exists, frost forms, and temporary salty liquids may occur under limited conditions. But modern Mars is not a second Earth waiting beneath red dust. Its landscape, however, records a different past. Dry valley networks, ancient lake beds, rounded sediments, and minerals formed in water show that liquid water once moved across the surface. Robotic missions have found environments that once included rivers, deltas, and long-lived lakes. Mars therefore demonstrates that a world can satisfy important conditions during one era and lose them during another. Several processes contributed to that change. Mars is smaller than Earth, so its gravity is weaker and its interior cooled differently. The planet lost the global magnetic field it possessed early in its history. Solar radiation and charged particles helped remove atmospheric material over time. Water became trapped as ice, bound into minerals, or lost to space. As the atmosphere thinned, it held less heat and made stable surface liquid water increasingly difficult. This does not prove that a magnetic field is strictly required for habitability, nor that small planets must become barren. Atmospheric escape depends on many connected properties: gravity, temperature, chemistry, stellar radiation, replenishment from the interior, and time. Mars matters because it reveals the cumulative result of those processes, not because it supplies one simple rule. Together, Venus, Earth, and Mars establish the first three gates in our journey. The first is energy. Does the planet receive an amount of stellar radiation compatible with liquid water under any reasonable atmosphere? The second is the planetary body. Does it have the gravity, composition, and interior history needed to support a lasting environment? The third is the atmosphere. Does enough gas exist, with suitable pressure and chemistry, to control heat and allow water to remain stable? Passing one gate cannot substitute for failing another. Venus has a substantial rocky body and atmosphere, but its climate makes surface water impossible today. Mars preserves evidence of water and occupies the colder side of the Sun's broad habitable region, but its present atmosphere cannot sustain widespread surface liquid. Earth passes all three gates, yet only through the interaction of systems that evolved across billions of years. When astronomers study an exoplanet, they usually know the orbit before they know the atmosphere. They may estimate the planet's size, while remaining unable to tell whether it resembles Earth, Venus, Mars, or none of them. The solar system supplies the warning that must accompany every distant candidate. Worlds receiving broadly promising energy can follow opposing paths. Scientists needed a way to convert these local lessons into predictions for stars of different brightness and color. They needed to identify where water loss and carbon dioxide warming might fail around different stars. It modeled where the energy gate could remain open for distant worlds, the habitable zone. The habitable zone is often drawn as a green band around a star, with a hot red region inside and a frozen blue region beyond it. The image is useful, but it can create the wrong impression. Nature does not paint a boundary in space. A planet does not cross an invisible line and suddenly gain an ocean. The band is a model, an attempt to calculate where a suitable rocky world could keep liquid water exposed on its surface. To turn that idea into a scientific tool, researchers needed to calculate how an atmosphere responds as stellar energy changes. In 1993, James Casting, Daniel Whitmire, and Ray Reynolds published a climate modeling study that became a foundation of the modern habitable zone concept. Their work did not search for life. It asked a more limited and testable question. Over what orbital range could a rocky planet, with an atmosphere broadly comparable to Earth's, maintain surface liquid water? Their model represented a vertical column through a planetary atmosphere. It followed radiation entering from the star, energy leaving as infrared heat, and the way gases such as water vapor and carbon dioxide absorbed different wavelengths. A one-dimensional model could not reproduce every cloud, storm, continent, or ocean current. Its strength was different. By simplifying the planet, researchers could test many atmospheric conditions and many kinds of stars using the same physical framework. The inner boundary emerged from the behavior of water. As a planet receives more stellar energy, more surface water evaporates. Water vapor is itself a strong greenhouse gas, so additional vapor can increase warming and produce further evaporation. Under sufficiently intense conditions, the upper atmosphere becomes wet enough for sunlight to break apart water molecules efficiently. Hydrogen can then escape to space, gradually draining the planet's water supply. Under still stronger warming, a runaway greenhouse can evaporate an ocean and prevent the surface from cooling back into a stable liquid water state. These are related limits, not identical events, and their exact positions depend on assumptions. Clouds can reflect incoming light or trap outgoing heat. The amount of water, atmospheric pressure, planetary mass, rotation, and surface properties can alter the result. The inner edge is therefore not a single universal distance. It is a threshold estimated for a stated kind of planet around a stated kind of star. The outer boundary involves a different failure. Move an Earth-like world farther from its star, and lower temperatures allow more carbon dioxide to accumulate, without being rapidly removed by processes assumed in the model. Carbon dioxide strengthens greenhouse warming and can compensate for weaker sunlight. At first, adding more of it can keep surface water liquid at greater distances. Eventually, that remedy stops working. A dense carbon dioxide atmosphere can scatter increasing amounts of incoming starlight back into space. Carbon dioxide may also condense under sufficiently cold conditions. Beyond the maximum greenhouse limit, adding more carbon dioxide no longer raises the surface temperature enough to preserve widespread liquid water. This creates the classical model's conservative outer edge. The solar system supplied another pair of boundaries based on history rather than only climate calculations. Venus may once have retained water before reaching its present greenhouse state, so the orbit of early or recent Venus can inform an optimistic inner limit. Ancient Mars possessed rivers and lakes, even though modern Mars is cold and dry. So early Mars can inform an optimistic outer limit. These empirical boundaries widen the search, but they do not prove that every planet between them can sustain water today. In the years after the 1993 study, improved information about how water vapor and carbon dioxide absorb radiation allowed Ravi Kopparapu and colleagues to update the calculations. Their 2013 and 2014 work refined the stellar energy thresholds and examined how planetary mass could influence the inner boundary. The revisions did not overthrow the habitable zone. They demonstrated how a useful scientific model improves when its underlying data and physical assumptions improve. Distance in astronomical units cannot be copied directly from the solar system to every star. A dim red dwarf produces far less total energy than the Sun, so its habitable zone lies much closer. A brighter star places comparable energy farther away. Yet total energy is not the only difference. Stars of different temperatures emit different mixtures of visible, infrared, and ultraviolet light. Ice and snow reflect much of the visible light produced by stars like the Sun, but they absorb more of the near-infrared light common around cooler red stars. Water vapor and carbon dioxide also absorb particular wavelengths. As a result, the same total amount of stellar energy can produce different climate responses depending on the star's spectrum. Habitable zone calculations use stellar temperature as well as luminosity to estimate the relevant energy limits. The models also evolved beyond single atmospheric columns. Three-dimensional general circulation models can represent winds, day and night sides, regional humidity, clouds, oceans, and the effects of rotation. This is especially important for planets orbiting close to cool stars, where tidal interactions may cause one side to face the star for long periods. Atmospheric circulation could transport heat from the permanent day side toward the night side, while clouds above the illuminated region might reflect enough radiation to shift the inner boundary. Three-dimensional models are more detailed, but detail does not remove uncertainty. They require assumptions about continents, ocean depth, rotation, cloud behavior, atmosphere, and initial conditions that are unknown for most exoplanets. One-dimensional models can explore a wider range of possibilities with fewer planet-specific assumptions. The two approaches therefore answer complementary questions. One searches broad physical limits. The other investigates how particular planetary arrangements behave within them. This is why our 2026 atlas contains both an empirical habitable zone and a narrower boundary, based on three-dimensional climate work. The 45 rocky candidates occupy the broader empirical region. 24 remain within the narrower region. The difference is not a contest between a correct map and an incorrect one. It shows how the candidate population changes when the climate question becomes more restrictive. Uncertainty in the star can move the borders as well. Astronomers estimate a star's temperature, radius, and luminosity from observations. A revision to those values changes both the energy reaching a planet and the calculated location of the zone. Uncertainty in the planet's orbit, especially an elongated orbit, can complicate its average and seasonal irradiation. The green band should therefore be imagined as a set of tested shorelines, each labeled with assumptions, rather than one permanent ring. Near the inner shoreline, researchers can ask when water loss or runaway warming becomes likely. Near the outer shoreline, they can test the limit of greenhouse protection. Between them, Earth-like stellar energy offers a useful comparison but not an Earth-like verdict. By the beginning of the exoplanet era, scientists had constructed a rule capable of being applied to other stars. It was limited, transparent, and revisable. That was precisely why it was valuable. The model did not identify inhabited planets. It told astronomers where a necessary condition for exposed liquid water might survive, and where observations could challenge the theory. For years, however, the rule had more predictive territory than known worlds to occupy it. Astronomers could calculate habitable zones around countless stars, while possessing few small planets to place inside them. The next breakthrough would not come from making the green band more visually convincing. It would come from watching thousands of stars at once and detecting the faint, repeated shadows of planets crossing in front of them. For most of the 20th century, the habitable zone surrounded stars that had no known planets. Astronomers could calculate where a temperate orbit should lie, but they could not show whether small worlds occupied it. The first exoplanets revealed an unexpected population, including massive planets moving extremely close to their stars. These discoveries proved that planetary systems were real and diverse, yet they did not answer how often something closer to Earth might occur. The central difficulty was scale. A planet like Earth is dim beside its star and does not produce its own visible light. At interstellar distances, the planet and star appear almost at the same point. Photographing the world directly requires separating an extremely faint signal from overwhelming glare. Early searches, therefore, relied on indirect effects: the planet's gravity, moving its star, or the planet briefly blocking part of the star's light. The transit method turns that second effect into a survey. If a planet's orbit happens to align with our line of sight, the planet passes between its star and Earth. The star then dims by a tiny but measurable amount. When the same dip repeats at regular intervals with the same shape and depth, astronomers can infer an orbiting body. The time between dips reveals the orbital period. The amount of blocked light helps estimate the planet's radius relative to its star. One transit is not enough. Stars vary for many reasons, including spots, flares, pulsations, and nearby blended stars. Instrumental changes can imitate weak signals. Researchers require repeated events, careful processing, and follow-up observations to distinguish a planet from noise or an eclipsing stellar companion. Even then, the transit reveals a silhouette, not a landscape. It measures how much of the star disappears, not what exists beneath the planet's clouds or on its ground. NASA's Kepler mission was designed to make this method statistical. Launched in 2009, the telescope watched the brightness of more than 100,000 stars in a fixed region of the sky. Instead of choosing only a few promising systems, it searched continuously for recurring patterns. Its precision allowed it to detect smaller planets and longer orbits than surveys dominated by giant worlds close to their stars. The strategy changed the question. Astronomers no longer asked only whether another star possessed a planet. They could begin asking how planet size and orbital period were distributed across a large population. Kepler revealed systems containing multiple planets, worlds between Earth and Neptune in size, and small bodies receiving levels of stellar energy associated with habitable zone conditions. Kepler 22b became an early symbol of that transition. Its orbit lies in the habitable zone of a star broadly similar to the Sun, and its discovery showed that Kepler could identify a planet in the kind of orbit the mission was built to find. But its radius is more than twice Earth's, leaving open whether it possesses a rocky surface, a deep ocean, or a substantial envelope of gas. A promising orbit did not settle its physical nature. Kepler 186f provided a different milestone. It was the first roughly Earth-sized planet identified in the habitable zone of another star. Its size made a rocky composition more plausible, but it orbits a cool red dwarf and receives less stellar energy than Earth. Its mass, atmosphere, water inventory, and surface conditions remain uncertain. The discovery supplied 2 early passport stamps while leaving the decisive pages blank. Kepler 442b receives stellar energy closer to Earth's and falls within modern habitable zone selections. Kepler 452b travels around a star more similar to the Sun, on an orbit lasting a little longer than an Earth year. Public descriptions called it an older cousin of Earth. Yet its estimated radius places it near a transition, where a planet might be rocky, or might retain a volatile envelope. In the 2026 catalog, its status also carries a controversy flag. Familiar numbers do not remove measurement uncertainty. These examples demonstrate why the Kepler revolution cannot be summarized as the discovery of a series of Earth twins. Its deeper achievement was population science. The mission showed that planets are common, that compact systems are widespread, and that small planets occur in many environments. It supplied enough detections for astronomers to estimate how frequently particular kinds of worlds appear, while also revealing how strongly every estimate depends on what the telescope was capable of seeing. Transits contain a built-in geometric bias. Most planetary orbits do not pass directly across their stars from our viewpoint. A planet can exist without ever producing a transit. Close in, planets are more likely to align and cross frequently. A world completing an orbit in a few days produces many repeated events during a mission. An Earth analog around a Sun-like star transits only once each year, and several years of observation are needed to establish a reliable repeating pattern. Size creates another bias. A giant planet blocks much more starlight than an Earth-sized body. A small planet crossing a small red dwarf produces a stronger relative dip than the same planet crossing a large Sun-like star. This makes compact red dwarf systems especially favorable for discovery and later atmospheric observation. It also means that the best represented planets in the catalog are not necessarily the most common planets in the galaxy. Noise and stellar behavior add further selection effects. Active stars can hide shallow transits. Distant stars provide fewer photons and weaker measurements. Long-period planets may transit too few times. Data pipelines must decide which signals deserve follow-up, and confirmation can require years. When astronomers calculate planet occurrence, they must estimate not only how many planets Kepler found, but how many similar worlds it would have missed. Kepler's field was narrow and distant, so its legacy also shaped a different strategy. Later surveys, such as TESS, searched much larger areas of sky, emphasizing brighter and often nearer stars. Their purpose was not simply to repeat Kepler's census. Nearby bright hosts offer stronger opportunities for follow-up measurements from ground observatories and space telescopes. The result is a bridge between population discovery and individual characterization. Kepler showed that small planets are plentiful, while newer surveys identify targets. This is why the occurrence rate of true Earth analogs around Sun-like stars remains difficult to pin down. The population is hiding where the survey is least complete. Small radii, long orbital periods, and tiny signals. Kepler demonstrated that small planets are abundant, but the exact frequency of a rocky Earth-sized world receiving Earth-like energy around a star like the Sun depends on definitions, detection efficiency, stellar measurements, and statistical treatment. The catalog also changes when information about a host star improves. A transit gives the planet's size relative to the star. If astronomers revise the star's radius, they must revise the planet's radius. A better estimate of stellar luminosity changes how much energy reaches the planet and may move it across a habitable zone boundary. Gaia's precise stellar measurements, therefore, reshape the meaning of discoveries made years earlier. Kepler transformed the green bands from empty predictions into occupied territory. It revealed worlds near inner boundaries, outer boundaries, and levels of irradiation similar to Earth. Some appeared small enough to remain rocky candidates. Others proved too large or too uncertain. Every detection became both a possible destination and a test of the filters used to select it. Yet the mission's success sharpened the central contradiction. The number of possible worlds grew faster than our knowledge of any one of them. A transit could reveal radius and orbit with remarkable precision, while leaving atmosphere, surface pressure, temperature, water, and chemistry almost untouched. The map gained thousands of points, but most planetary passports still contained only the first entries. To proceed, astronomers needed more than discovery. They needed ways to measure mass, estimate composition, detect thermal radiation, and separate the fingerprints of atmospheric gases from the light of a star. They also needed to understand the mechanisms that could produce entirely different environments from the same measured size and orbit. The next stage of the journey therefore moves beneath the catalog, into the hidden climate machinery of a distant dot. Once a planet has been detected, its orbit and size can make it look familiar long before its environment is understood. An Earth-sized circle, placed inside a green habitable zone, invites the mind to add oceans, clouds, and continents. But those features are not contained in the measurements. Between the silhouette astronomers observe and the surface an illustration imagines lies a chain of hidden systems, any one of which can change the planet's fate. The first uncertainty is the body itself. Radius tells us how large a planet appears when it crosses its star. Mass tells us how strongly its gravity affects nearby objects or its host star. When both are measured, astronomers can calculate average density. A dense world may contain a large iron core and rocky mantle. A lower density planet could contain more water, ice, or gas. Yet density is an average. Different combinations of materials can produce similar values. A planet near Earth's radius is therefore more likely to be rocky than a world the size of Neptune. But likely does not mean known. Some planets may possess deep global oceans above high-pressure forms of ice. Others may carry thick, volatile envelopes that hide any solid surface beneath crushing pressure. Even a genuinely rocky world can have a core, mantle, crust, and chemical composition unlike Earth's. The passport's rockiness stamp is often an informed classification, not a photograph of ground. Gravity then influences what the planet can retain. A more massive world holds gases more strongly, but atmospheric survival is not determined by gravity alone. Molecules in the upper atmosphere move at speeds set partly by temperature. High-energy radiation from the star can heat that region, break molecules apart, and drive particles into space. Stellar winds and magnetic interactions can accelerate additional loss. Light gases escape most easily, but intense conditions acting over long periods can remove heavier material as well. An atmosphere can also be rebuilt. Volcanoes may release water vapor, carbon dioxide, nitrogen-bearing compounds, and other gases from the interior. Impacts can deliver volatiles or remove them. Chemical reactions can lock gases into rocks, while surface heating can return them to the air. A planet observed today may carry its original atmosphere, a secondary atmosphere produced later, a thin remnant, or almost nothing. Its present orbit does not reveal which history occurred. The star's age makes that history especially important. Young stars can behave differently from mature ones. Red dwarfs remain active for long periods, and may produce strong ultraviolet and X-ray radiation during the era when close-orbiting planets are losing heat and forming atmospheres. They also pass through a bright early phase. A planet that receives moderate energy today may have endured enough early radiation to lose large amounts of water before the star settled into its present state. This creates two planets in one orbit. The world climate models calculate using current starlight, and the world produced by billions of years of stellar evolution. If the planet began with a large water supply, received later delivery, or released volatiles from its interior, habitable conditions might remain possible. If those reservoirs were small, the same present-day orbit could contain a dry rock. Current energy is only the final frame of a much longer film. Close habitable zones introduce another mechanism: tides. A planet orbiting near a low-mass star experiences a strong difference in the star's gravitational pull across its body. Over time, that interaction can alter rotation and may lead toward a state in which the same hemisphere repeatedly faces the star. One side would then receive continuous daylight while the other remains dark. This image once encouraged a simple conclusion. The day side would burn, the night side atmosphere would freeze, and only a narrow twilight ring might remain mild. Three-dimensional climate models show that the outcome is not so automatic. A sufficiently substantial atmosphere can carry heat through winds. An ocean can transport additional energy. Bright clouds forming above the region of strongest heating can reflect starlight. Under some conditions, a synchronously rotating planet could maintain broad areas of moderate temperature. That possibility does not make tidal locking harmless. Atmospheric pressure and composition determine how well heat moves. Water may become trapped as ice on the night side. Stellar activity can interact with the upper atmosphere. Tidal forces can also generate internal heating, which may support geology or become excessive. Rotation is one part of a coupled climate, not a single switch marked habitable or dead. Water itself creates another set of hidden outcomes. Too little water can leave a dry surface where climate regulation operates differently from Earth's. A moderate inventory can produce oceans and continents, exposing rock to weathering and allowing nutrients to circulate. A much larger inventory may cover the entire planet. Beneath a deep ocean, pressure can create exotic ice phases that separate liquid water from the rocky interior, potentially limiting chemical exchange. No telescope has mapped the global water inventory of an Earth-sized habitable zone exoplanet. Even if water vapor is eventually detected in an atmosphere, it will not automatically prove that oceans cover the surface. Vapor can arise under hot conditions, from limited reservoirs, or above clouds that conceal deeper layers. The location, quantity, phase, and persistence of water all matter. Geology connects many of these systems. Earth's long-term carbon exchange involves weathering, sediments, volcanism, and the movement of the crust and mantle. This can provide stabilizing feedback across geological time. But exoplanet plate tectonics cannot normally be observed, and scientists do not know whether Earth's specific style of tectonic activity is common, rare, or necessary for long-lived surface habitability. Internal heat may persist through radioactive decay, formation energy, and tidal effects. It can drive volcanism and chemical cycling. Too little activity may reduce atmospheric replenishment. Too much can create intense resurfacing or atmospheric change. Once again, the relevant question is not whether geology is simply present. It is whether the rate, chemistry, and history support a stable environment. Magnetic fields are often treated as another compulsory passport stamp. Earth's magnetic field deflects many charged particles from the solar wind, and Mars lost its global field before much of its atmosphere disappeared. Yet those facts do not establish a universal rule that every habitable planet requires an Earth-strength magnetic shield. Atmospheric escape depends on several pathways, and magnetic fields can redirect charged particles in complicated ways. A planet's gravity, atmosphere, star, and replenishment history must be considered together. Clouds demonstrate how a small unknown can transform a climate verdict. They can reflect incoming starlight and cool the surface. They can also absorb outgoing infrared energy and warm it. Their altitude, particle size, coverage, and composition determine which effect dominates. Around a synchronously rotating world, a persistent bright cloud deck near the substellar point might protect the surface from intense radiation. Different assumptions about clouds can therefore move the modeled inner habitable zone edge. The chemical composition of the air matters beyond its greenhouse effect. Nitrogen can provide pressure and influence heat transport without strongly absorbing infrared radiation. Carbon dioxide and water vapor regulate temperature across broad conditions. Other gases can add warming or participate in photochemical reactions. Oxygen, if detected, would demand careful interpretation because non-living processes can produce it under some circumstances. No single atmospheric molecule can carry the full weight of a habitability claim. Time unifies all these variables. A planet may briefly pass through clement conditions or maintain them for billions of years. Its star slowly changes brightness. Its interior cools. Continents, oceans, and atmospheres evolve. Impacts interrupt climate. Life, if it begins, can alter atmospheric chemistry as it did on Earth. Habitability is not only a place within an orbit. It is a relationship that must persist long enough and steadily enough for the environmental question being asked. This hidden machinery explains why two planets with the same radius and stellar energy need not resemble each other. One may retain a dense greenhouse atmosphere. Another may be airless. A third may circulate heat beneath global clouds. A fourth may hide its water under ice or above a high-pressure mantle. Their early passport stamps can match, while every later page diverges. The problem is not that these mechanisms make the search hopeless. They make it experimental. Each hidden property produces effects that observations may constrain. Mass and radius narrow interior possibilities. Changes in planetary brightness can reveal heat transport. Filtered starlight can test atmospheric gases. Thermal emission can distinguish some thick atmospheres from bare surfaces. Stellar observations can measure the radiation environment that shapes atmospheric loss. Most candidates will remain combinations of possibilities until several observations agree. A radius alone leaves composition uncertain. A spectrum alone may be flattened by clouds or contaminated by the star. A temperature measured on one hemisphere may not describe the whole climate. Confidence grows when independent methods converge, closing alternatives instead of adding another suggestive clue to evidence. Our journey has now descended from a green orbital band into a coupled planetary machine. The first gate supplies energy. The remaining gates determine what that energy becomes. To discover which candidates possess more than favorable orbits, astronomers must extract separate pieces of evidence from signals almost buried in starlight. The next question is no longer where the planets are. It is how invisible worlds can be weighed, measured, and tested from light years away. An exoplanet rarely arrives as one complete discovery. It is assembled from separate measurements, each revealing a different property and carrying a different limitation. One instrument detects a repeating shadow. Another measures the motion of the star. A third separates wavelengths of light. The planet we describe is the point where those signals begin to agree. The transit method supplies the most familiar starting point. As a planet crosses its star, it blocks a fraction of the stellar disk. The depth of that dimming gives the planet's radius relative to the star. Repeated transits establish the orbital period, while their duration and shape provide information about the path across the star. Once the star's own size is known, the relative measurement becomes an estimated planetary radius. That last step explains why stellar astronomy is part of planet science. If the estimated radius of the star changes, the calculated radius of the planet changes with it. Better measurements from observatories such as Gaia can therefore move a world above or below a catalog's Rocky size limit. Improved stellar luminosity also changes the energy assigned to the planet, and may alter whether its orbit falls inside a selected habitable zone boundary. Radius alone cannot tell how much matter the planet contains. For that, astronomers often use radial velocity. A planet and star orbit a shared center of mass. The star's motion is far smaller, but part of it may carry the star toward Earth, and then away again. This motion shifts features in the stellar spectrum through the Doppler effect. The repeating shift reveals the planet's gravitational influence. Radial velocity provides an estimate of mass, but viewing geometry matters. Unless the orbital inclination is known, the method usually yields a minimum mass rather than the exact value. A transiting planet provides the alignment needed to constrain inclination, allowing transit and radial velocity measurements to reinforce one another. Radius plus mass gives average density, narrowing the range of possible interiors. In tightly packed systems, planets also reveal one another through timing. If every planet followed an isolated orbit, each transit would arrive on a perfectly regular schedule. Neighboring planets tug on one another, making some transits occur slightly early and others slightly late. These transit timing variations can estimate planetary masses and orbital interactions, even when the star's own motion is difficult to measure. They have been especially valuable in multi-planet systems such as TRAPPIST-1. With orbit, radius, and mass, a planetary passport becomes more detailed, but atmosphere remains another investigation. During a transit, a tiny portion of starlight passes through any gases surrounding the planet before reaching the telescope. Molecules absorb particular wavelengths, so the planet appears slightly larger at colors where its atmosphere blocks more light. Separating the star's spectrum before and during transit can reveal this pattern. The method is called transmission spectroscopy. The description sounds direct, but the atmospheric signal can be extremely small. Clouds or hazes may hide deeper molecular features. The star is not a uniform lamp. Spots, bright regions, and changing activity can introduce wavelength patterns that resemble or distort planetary absorption. Researchers must observe multiple transits, model the star, compare instruments, and test whether an apparent feature persists. A flat transmission spectrum does not automatically prove that no atmosphere exists. It can indicate high clouds, haze, a compact atmosphere, contamination, or insufficient precision. Thermal emission provides a different route. A planet gives off infrared energy according to its temperature and atmospheric behavior. When a planet passes behind its star, the combined light of star and planet briefly loses the planet's contribution. Subtracting the star-only signal from the earlier total can isolate the planet's dayside emission. This secondary eclipse is difficult to measure for a small rocky world, but it can constrain temperature and reject some atmospheric scenarios. A bare rock with little heat redistribution may have a hot dayside because absorbed energy is released near where it arrives. A substantial atmosphere can transport energy toward the night side, reducing the contrast. Yet one temperature measured through one wavelength band does not reconstruct the whole climate. Surface composition, clouds, and atmospheric absorption can produce overlapping outcomes. The result is strongest when several wavelengths and independent methods converge. Observing a planet throughout its orbit creates a phase curve. Just as the Moon shows phases, the fraction of an exoplanet's illuminated hemisphere visible from Earth changes. Measuring the system's brightness across the orbit can reveal how energy is distributed between day and night. A strong contrast may suggest weak heat transport. A smoother pattern may indicate atmospheric or oceanic circulation. For tiny temperate planets, the required precision remains formidable. Direct imaging tries to separate planetary light from starlight, rather than waiting for a transit. The challenge combines contrast and angular separation. A rocky planet reflects or emits vastly less light than its star, and from Earth, the two may appear extremely close together. Coronagraphs or other techniques must suppress the star's glare while preserving the faint signal nearby. Closer planetary systems and wider apparent orbits are generally more favorable, but instrument performance and wavelength also matter. These methods explain why different candidates rise to the top of different observing lists. TRAPPIST-1, D, E, F, and G transit a very small star, giving comparatively strong signals for their size. LHS 1140b also transits and has both mass and radius measurements, making it a valuable target for atmospheric study. Proxima Centauri b is much closer to Earth, but it does not offer the same established transit opportunity. Its proximity and apparent separation make it important for future techniques capable of isolating planetary light. The published 2026 catalog compares targets using metrics designed for these distinct tasks. For transiting worlds, a transmission spectroscopy metric estimates which atmospheres may produce stronger accessible signals. For potential direct imaging, angular separation and estimated planet-to-star contrast become central. A world can rank highly for one method and poorly for another. Scientific priority is therefore not a universal beauty contest. It depends on the question and the instrument. Null results are part of this process. If observations fail to show the signal expected from a thick, hydrogen-rich atmosphere, that scenario becomes less likely. If thermal emission is inconsistent with a dense carbon dioxide atmosphere that efficiently redistributes heat, researchers can reject that model under the tested assumptions. The planet does not become uninteresting. Its range of possible identities becomes narrower. This is crucial for rocky planets because their small signals permit cautious conclusions. An observation may rule out a clear, extended atmosphere while leaving a thin secondary atmosphere possible. It may disfavor a Venus-like state without determining whether the surface is bare. Scientific language must follow the measurement. The data constrain specific atmospheric models. They do not grant permission to announce a complete planetary environment. Stellar observations provide another essential layer. Ultraviolet and X-ray measurements reveal the radiation capable of heating and eroding upper atmospheres. Monitoring flares establishes how often energetic events occur. Stellar age estimates help reconstruct the planet's exposure over time. Without this context, even an atmospheric spectrum is incomplete, because the same composition may be stable around one star and temporary around another. No single technique completes the passport. Transit photometry supplies radius and orbital geometry. Radial velocity or timing supplies mass. Their combination constrains density. Transmission spectroscopy tests the limb of an atmosphere. Secondary eclipses and phase curves examine thermal behavior. Direct imaging may eventually provide reflected light spectra. Stellar measurements define the environment acting on the planet. Each method closes some possibilities and leaves others open. Evidence also improves through repetition. One transit may contain noise that resembles atmospheric absorption. Several visits can reveal whether the pattern returns. Observations at different wavelengths test different molecules and atmospheric depths. Separate research teams can process the same data with different assumptions. Agreement does not remove uncertainty, but strong claims must survive different instruments, analyses, and models before becoming genuinely reliable evidence about a distant planetary atmosphere. The most persuasive future case for habitability will therefore emerge from convergence. A planet should appear rocky through bulk measurements. Its atmosphere should be detected and characterized rather than assumed. Temperatures and heat transport should remain compatible with liquid water. Atmospheric chemistry should make sense in the context of the star and the planet's history. Independent observations should tell one physical story. We are now equipped to visit the nearest and most celebrated candidates without confusing illustrations with evidence. Proxima Centauri b offers extraordinary proximity but limited direct knowledge of its atmosphere. TRAPPIST-1 offers several rocky transiting worlds and the first detailed tests from Webb. These systems should have made the search simple. Instead, they reveal why the easiest planets to detect can be among the hardest places to keep air and water. The nearest star beyond the Sun is Proxima Centauri, a faint red dwarf only about 4.2 light-years away. In 2016, astronomers detected a planet through the repeated motion it produced in the star. Proxima Centauri b has a minimum mass close to Earth's and completes an orbit in just 11.2 days. Because its star is small and cool, that tight orbit still places the planet within a habitable zone range. No known habitable zone exoplanet is closer. That fact makes Proxima b feel almost reachable. as though distance itself should guarantee knowledge. Yet the planet does not transit from our viewpoint, so astronomers do not have a directly measured radius from a passing shadow. Its mass comes from radial velocity and depends on orbital orientation. Most importantly, no observation has established whether it possesses an atmosphere, liquid water, or a stable surface climate. The host star turns proximity into a more difficult question. Proxima Centauri is magnetically active. It produces flares and high-energy radiation capable of heating and eroding a planetary upper atmosphere. Models show that an Earth-like atmosphere in such an environment could be lost far more rapidly than Earth's air is lost to the Sun. But this is a modeled risk, not a direct observation of a bare Proxima b. Several histories remain possible. The planet may have lost much of its early atmosphere and water. It may have begun with a larger volatile supply, rebuilt an atmosphere through geological activity, or retained gases under conditions different from Earth. Its rotation and heat transport are also not directly known. Proxima b therefore holds two strong passport stamps: nearby orbit and Earth range minimum mass, while the atmospheric and water pages remain blank. At roughly 40 light-years, the TRAPPIST-1 system is farther away but offers a different advantage. 7 planets cross the face of an ultra-cool red dwarf from our perspective. All are close to Earth in size, and their gravitational interactions allow astronomers to estimate masses through transit timing. Several occupy or approach the system's habitable zone. The result is not one isolated candidate, but a comparative planetary laboratory. The 7 worlds orbit so close to their star that the entire system would fit comfortably inside Mercury's orbit around the Sun. Their years last days rather than months. TRAPPIST-1 D, E, F, and G appear in the published Rocky Habitable Zone catalog, while E, F, and G are commonly emphasized as temperate members. Their measured masses and radii produce densities broadly consistent with rocky compositions, though interior models still allow different amounts of water and iron. Because all 7 planets formed around the same star, they allow a powerful comparison. Each experienced the star's broad history, but each receives a different level of radiation. Inner planets test atmospheric loss and intense heating. Temperate planets test whether air and water can survive farther out. Differences among them can reveal how orbital energy, mass, composition, and atmospheric history interact. Before Webb, illustrations easily filled those possibilities with familiar landscapes. One world might be shown as a humid ocean planet, another as a cold blue Earth, and another as a desert with a red sun. These images represented modeled scenarios, not observations. Webb began replacing some of those possible surfaces with actual constraints. TRAPPIST-1b is the innermost planet and is not a habitable zone destination, but it provides an early stress test for the system. Webb measured the planet's thermal emission when it passed behind its star. Its dayside temperature was about 500 kelvins, and the measured heat was consistent with a world lacking a significant atmosphere capable of redistributing energy. A thick atmosphere did not match the result. TRAPPIST-1c offered another comparison. It is similar in size to Venus and receives a comparable amount of stellar energy. Researchers tested whether it might possess a thick carbon dioxide atmosphere like Venus. Webb's thermal measurement disfavored that scenario. The result remained consistent with a bare rocky surface or a very thin carbon dioxide atmosphere without thick clouds. It did not reveal an Earth-like environment, but it eliminated an attractive planetary analogy. These results changed the meaning of atmospheric absence. Before measurement, almost any atmosphere could be placed around an Earth-sized circle in a model. After measurement, specific thick atmospheres became difficult to defend for B and C. The blank passport pages did not suddenly become complete, but the range of acceptable entries narrowed. The temperate planets require even greater care. As of 2026, Webb had published results concerning TRAPPIST-1D and E, as well as B and C, while work across the system continued. Each observation uses particular wavelengths and tests particular models. A featureless spectrum, a thermal constraint, and a detected molecule would answer different questions. Conclusions about the hot inner planets cannot simply be copied onto E, F, or G. The system may share aspects of formation and stellar exposure, but the planets differ in mass, orbit, irradiation, and possibly volatile history. An inner world can lose an atmosphere, while an outer sibling retains one. Alternatively, common formation conditions may leave several planets dry. Only planet-specific observations can distinguish those histories. This is the midpoint at which our original map changes meaning. Until now, the journey could appear to be moving from broad orbital rules toward increasingly Earth-like destinations. Proxima b seemed important because it is close. TRAPPIST-1 seemed promising because its planets are small, rocky, and temperate. Better instruments were expected to reveal which familiar version of Earth each world resembled. The evidence replaces that expectation with a deeper investigation. The most accessible candidates often orbit small red stars, because those stars make planetary signals easier to detect. The same close orbits and active stellar environments may threaten the atmospheres required for surface water. Observational advantage and environmental risk are connected. This does not turn Proxima b or the TRAPPIST-1 planets into failed worlds. A failed Earth analogy is not a failed scientific target. Proxima b tests whether a nearby planet around an active star can retain or rebuild air. TRAPPIST-1 allows several rocky planets to be compared under one stellar history. A null atmospheric result teaches us which evolutionary paths did not occur and which possibilities remain. Their value therefore lies in becoming less imaginary. Each observation moves a world away from an unrestricted artist's impression and toward a physical case. The passport is completed not only by positive detections, but by exclusions. No thick hydrogen envelope, no Venus-like atmosphere under the tested conditions, no efficient heat redistribution of a certain kind. Removing a possibility is progress when the alternatives are clearly stated. The governing question must now change. We are no longer asking which dots sit inside a habitable zone and look approximately Earth-sized. We are asking which planets could preserve the atmosphere, water, and climate that make the zone meaningful, especially around the red dwarfs dominating the accessible sample. That reversal makes the second half of the journey more demanding. A candidate must now survive not only a geometric selection, but an evolutionary one. Its present orbit must be read alongside the star's past, its possible atmosphere, and the measurements capable of distinguishing survival from loss. Closeness provides opportunity. To answer that, the journey must follow these systems backward through time. It must confront the bright youth of low-mass stars, repeated flares, atmospheric escape, tidal rotation, and the possibility of secondary atmospheres. It must also preserve the counterexamples in which circulation, large volatile inventories, or geological replenishment allow survival. The nearest worlds have not ended the search. They have removed its easiest story. Red dwarfs dominate our present atlas for two connected reasons. They are the most common kind of star in the galaxy, and their small size makes nearby rocky planets easier to detect. A planet crossing a red dwarf blocks a larger fraction of the stellar disk than the same planet crossing a sun-like star. Because the star is faint and cool, its habitable zone lies close, producing frequent transits and short observing cycles. Those advantages explain why systems such as Proxima Centauri, TRAPPIST-1, LHS 1140, TOI 700, GJ 1002, and T-Garden Star appear so often in the search. They do not prove that red dwarf planets are the galaxy's best homes for life. They show that our instruments can find and test them more readily than an Earth analog taking a year to cross a larger, brighter star. The same close orbit creates the first concern. A red dwarf's habitable zone planet may circle at a small fraction of Earth's distance from the Sun. The planet experiences a stronger tidal interaction and sits directly inside the star's space weather environment. Flares can release ultraviolet and X-ray radiation. Charged particles and stellar wind interact with the upper atmosphere. Repeated across millions or billions of years, these effects can alter or remove planetary gases. The most dangerous period may occur early. Low-mass stars spend a long time contracting before reaching their stable main-sequence state. During this phase, they can be brighter relative to the habitable zones they will later possess. A planet occupying today's temperate orbit may once have received enough energy to drive a runaway greenhouse. Water vapor reaching the upper atmosphere could be split apart, allowing hydrogen to escape and leaving the world dry before current conditions began. This history challenges the habitability map because the present orbit can look ideal after the decisive loss has already occurred. A model using only today's stellar brightness may describe temperatures compatible with liquid water, while the actual planet carries the consequences of an earlier ocean's disappearance. The passport requires a history page, not only a current energy stamp. Atmospheric escape, however, is not one universal outcome. The rate depends on stellar radiation, planetary gravity, atmospheric composition, magnetic interactions, and replenishment. A world with a large initial water supply may survive losses that would desiccate a drier planet. Volcanic outgassing may build a secondary atmosphere after the most violent stellar period. Impacts can add volatiles later. Cooler outer planets in the same system may retain more than their inner siblings. Tidal rotation is similarly conditional. Close planets may rotate slowly or present the same side toward the star, but a permanent day side does not automatically create a permanent desert. Climate simulations show that sufficient atmosphere can move heat toward the night side. Oceans can contribute circulation. Reflective clouds may form over the hottest region. Under some conditions, the day side avoids runaway warming, while the night side avoids atmospheric collapse. Other conditions produce less favorable results. A thin atmosphere may transport too little heat. Water can freeze into deep night-side deposits. Intense radiation can damage atmospheric molecules and accelerate escape. Tidal heating can support geology, but excessive heating may drive extreme volcanism. These competing pathways are why scientists cannot responsibly declare all red dwarf planets habitable or sterile as a class. LHS 1140b illustrates the value of a target that can test several possibilities. It transits a nearby red dwarf and has both mass and radius measurements. Its density confirms that it is a substantial world, while its atmospheric state and water inventory remain subjects of investigation. In the 2026 catalog, it ranks among the stronger transiting targets. Its importance comes from measurable properties, not from a confirmed ocean. 2i700 provides another comparative system. Planets D and E are small transiting worlds receiving habitable zone levels of energy from a relatively quiet red dwarf. Their transits make them candidates for continued observation, although atmospheric characterization remains difficult. Their host's behavior offers a contrast with more active systems, allowing astronomers to ask whether quieter red dwarfs produce better chances for atmospheric survival. LP 890-9c lies in the habitable zone of an ultra-cool star and ranks favorably by estimated contrast among transiting rocky candidates. Its position makes it useful for testing climates near a cool star, but size and orbit cannot decide whether it is a temperate rocky planet, a greenhouse world, or something else. The candidate is valuable because these alternatives can eventually be confronted. Several nearby planets do not transit but are attractive for future direct observation. GJ 1002b and C orbit a red dwarf close enough to offer favorable separation and contrast compared with distant Kepler worlds. GJ 1061c and D, Wolf 169b, Ross 508b, GJ 273b, and Teegarden Star C occupy different regions of the empirical zone. Their minimum masses and stellar energy make them candidates, while unknown radii and atmospheres limit the claims. Each can be organized by the question it tests. GJ 1002, C, and other outer edge worlds probe how far greenhouse warming might extend surface habitability. Worlds near the inner edge test water loss and cloud feedback. TRAPPIST-1e, Proxima b, GJ 1061d, GJ 102b, and Wolf 1069b receive stellar energy broadly comparable to Earth's under the catalog's criteria. Similar energy creates a controlled comparison, not an expectation of similar surfaces. The distinction between observed risk and modeled outcome must remain visible. Stellar flares are observed. High-energy radiation is measured. Atmospheric escape follows established physical processes. But the claim that a specific planet has lost all its air usually remains an inference, unless atmospheric observations support it. Conversely, placing a planet around a quiet star does not prove that it retained an ocean. Even within the red dwarf class, labels such as active and quiet describe present measurements, not complete histories. A star that appears calm today may have exposed its planets to stronger radiation when young. A flare-rich star may host a planet with enough gravity or replenishment to retain air. Age estimates, ultraviolet monitoring, and atmospheric observations must be combined. This prevents the host star from becoming another shortcut. Stellar behavior changes the probability of habitability, but the planet's own response determines the environmental result. Time remains another crucial variable. The debate, therefore, concerns probabilities and histories rather than two absolute camps. One view emphasizes prolonged stellar activity, early runaway greenhouse conditions, and atmospheric erosion. Another emphasizes massive initial volatile reservoirs, atmospheric rebuilding, heat circulation, and protected or subsurface environments. Both rely on real mechanisms. Their relevance changes from planet to planet. This is why a single Earth similarity score cannot organize the journey. A planet may match Earth's radius while orbiting a far more active star. Another may receive nearly identical total energy but absorb a redder spectrum. A third may have an accessible atmosphere but lie close to a climate boundary. Ranking requires the scientific question: atmosphere detection, direct imaging, inner edge climate, outer edge greenhouse, eccentricity, or evolutionary age. Uncertainty itself becomes useful when it is structured. If better stellar measurements move a planet into or out of the zone, the world tests the precision of the boundary. If a spectrum rules out a thick atmosphere, it narrows the survival history. If several planets around one star differ, their shared environment helps isolate mass and orbit. The catalog becomes a set of experiments, rather than a collection of imagined destinations. The concentration of red dwarf targets also reveals what the catalog is missing. Planets like Earth around Sun-like stars produce weaker, less frequent transits and smaller radial velocity signals. Many may remain undetected, while known examples are often too distant for atmospheric study. The current atlas is therefore not a fair sample of all potentially habitable planets. It is a sample shaped by time, geometry, stellar brightness, and instrumental sensitivity. A future census may shift attention toward quieter orange and yellow stars, without making today's red dwarf experiments irrelevant or obsolete. Red dwarfs have therefore not supplied a final answer about life. They have supplied the first population where rocky habitable zone planets can be compared and, in favorable cases, characterized. Their risks are not reasons to discard them. Their abundance is not a reason to assume success. They are the environments in which theories of atmospheric survival can meet observations soonest. The next task is to reorganize the complete atlas around that experimental value. Every nominal candidate must appear, but not every candidate deserves equal narrative weight. Some provide strong transit signals. Some offer wider angular separation. Some sit at the thermal edges. Some receive Earth-like energy. Others enter only when uncertainties are included. By grouping worlds according to what they can test, the list of 45 becomes a coherent investigation rather than a roll call. The catalog we now enter is not arranged like a travel brochure. Its worlds are not ranked by how blue, green, or familiar they might appear. They are organized by the measurements they offer and the limits they can test. This is how a list of 45 rocky habitable zone candidates becomes an atlas of experiments. The catalog began with data from the NASA Exoplanet archive and updated information about host stars from Gaia. Its snapshot contained more than 6,000 confirmed planets. Researchers first identified 290 within an empirical habitable zone. They then retained transiting worlds no larger than twice Earth's radius and non-transiting worlds no more massive than 5 Earths. 45 met the nominal rocky and orbital criteria. 24 also remained inside a narrower three-dimensional climate zone. 27 of the 45 transit their stars. 15 of the 24 narrower zone worlds transit. This distinction matters because transiting planets can potentially be examined through filtered starlight, thermal eclipses, and timing. Non-transiting planets do not provide the same geometry, but nearby examples may offer wider apparent separation for future direct imaging. The atlas therefore divides immediately into different observational routes. The most information-rich group contains planets with measured mass and radius. In the published sample, 5 habitable zone worlds stand out with both values: LHS 1140b and TRAPPIST-1d, E, F, and G. These measurements allow density estimates and stronger tests of rocky composition. They do not reveal oceans or atmospheres, but they reduce one of the largest uncertainties affecting other candidates. The TRAPPIST-1 planets form a sequence rather than 4 isolated entries. Planet D lies toward the warmer region, while E receives energy closer to modern Earth. Planets F and G extend outward into cooler conditions. Because they orbit the same star, comparisons can limit differences in stellar age and composition. Their changing irradiation allows researchers to test how several rocky bodies responded to a broadly shared history. LHS 1140b supplies a different laboratory. It is larger and more massive than Earth, but remains inside the catalog's rocky limits. It transits a nearby small star, and its bulk measurements make it a high-priority atmospheric target. The key question is not whether it deserves the label ocean world from a model. It is whether observations can distinguish a retained atmosphere, a water-rich interior, or another physical state. Other transiting candidates broaden the climate experiment. TOI 700d and E orbit the same relatively quiet red dwarf and occupy different parts of its habitable region. LP 890-9 C circles an ultra-cool star and offers favorable estimated contrast. K23d and K2239d lie near the warmer side of the empirical zone. TOI 715b receives stellar energy close to Earth's under the catalog's comparison, while Kepler 1652b, Kepler 442b, Kepler 1544b, and Kepler 452b extend that Earth flux category across more distant systems. These names should not be heard as equal claims. A nearby bright host can support stronger follow-up than a faint, distant Kepler star. A precisely measured radius is more useful than a value carrying large uncertainty. Some planets have controversy flags in the archive or catalog. Kepler 452b and Kepler 186f, for example, must retain those cautions when presented. Catalog membership does not erase questions about detection or parameters. The inner edge offers a specific test. K2239d, TOI 700e, and K23d are among the transiting targets near that region, while Wolf 1061c and GJ 1061c provide non-transiting comparisons. Their value lies in probing the conditions under which water loss, clouds, and greenhouse feedback challenge surface habitability. A planet near the inner boundary is not automatically warmer Earth. It may help locate where Earth-like assumptions stop working. The outer edge asks the opposite question. TRAPPIST-1G, Kepler 186f, and Kepler 441b represent transiting candidates near the colder limit. GJ 1002c and GJ 667ce offer non-transiting cases. These worlds test whether dense carbon dioxide atmospheres, additional greenhouse gases, or climate circulation could preserve surface water under weak irradiation. Their atmospheres remain mostly unknown, so the test is still waiting for evidence. Between those shorelines lies the Earth flux comparison. TRAPPIST-1e, TOI 715b. Kepler 442b, Kepler 442b, Kepler 1544b, and Kepler 452b are transiting examples receiving energy within the catalog's selected range around modern Earth. Proxima Centauri b, GJ161d, GJ169b form nearby non-transiting counterparts. They allow the same question to be asked around stars of different temperature and activity. Does Earth-like total energy produce anything like Earth's climate? It may not. Redder starlight interacts differently with ice, water vapor, and atmospheric gases. Planetary masses, rotations, and histories differ. Some host stars flare. Others appear quieter today. Earth-like flux is therefore a controlled variable, not an environmental verdict. These candidates matter because they hold one input approximately constant, while other factors change. The direct imaging route emphasizes proximity and separation. Proxima offers the widest apparent separation among leading nearby rocky candidates in the catalog's comparison. GJ251c, Wolf 1061c, planets in the GJ667c system, GJ682b, and GJ273b also appear among useful targets when separation and estimated contrast are considered together. GJ3323b, GJ1061c, Ross 508b, GJ102b, and Teegarden Star C stand out in contrast-based rankings. These measurements describe feasibility, not habitability. A favorable contrast ratio means the planet may be less overwhelmingly faint beside its star at selected wavelengths. A larger angular separation means instruments have more space in which to suppress stellar glare. Neither indicates an atmosphere or water. They tell engineers and observers where a decisive measurement might be possible. The atlas also contains worlds whose category depends strongly on uncertainty. When researchers allowed the full reported ranges of stellar and orbital parameters to overlap the empirical zone, 9 additional candidates appeared. Gliese 12b, Kepler 399d, Kepler 438b, K272c, TOI 1452b, Kepler 138e, Ross 128b, and planets B and D around Teegarden Star. They are not part of the secure nominal 45 under the same definition. Their provisional status is scientifically useful. Better estimates of stellar temperature, radius, planetary orbit, and habitable orbit, or eccentricity, can determine whether they cross the boundary. If one leaves the zone, the result improves the map rather than invalidating it. If another enters, it becomes a stronger target. The uncertainty group shows how catalogs evolve through measurement rather than opinion. Some candidates also travel on eccentric orbits, changing their distance from the star during a year. Average stellar energy can place them inside a zone, while seasonal extremes create different climate pressures. Such worlds test whether climate stability depends only on average flux or on the timing and duration of heating. They remind us that a habitable zone is usually drawn with circles even when real orbits need not be circular. Age creates another layer. The published analysis identified 23 rocky habitable zone candidates with nominal age estimates older than Earth. Age does not make a world inhabited, but it changes the possible duration available for atmospheric evolution, geological cycling, and biology. An old planet may have enjoyed long stability or endured long erosion. Stellar and planetary history must decide between those outcomes. Seen together, The catalog becomes a matrix. One axis records the climate question: inner edge, Earth-like energy; outer edge, eccentric orbit, or long evolutionary time. Another records the observing method: transit spectroscopy, thermal measurement, radial velocity, timing, or future direct imaging. A third records confidence: nominal member, narrower zone member, controversial target, or uncertainty overlap candidate. The group structure also prevents distance from being confused with importance. A remote Kepler planet may be beyond atmospheric study today, yet still test how often small worlds occupy long-period orbits. A nearby radial velocity planet may be easier to separate from its star while lacking a known radius. A transiting world may offer atmospheric access, but orbit a faint, active host. No ranking solves every problem. The strongest atlas preserves these trade-offs, allowing one planet to test climate boundaries, another to test atmospheric survival, and another to test the limits of future instruments. Together, they describe the search more accurately than any single score could, while keeping every claim tied to the evidence available today and open to later scientific revision. Every planet occupies a position in that matrix, even when its narration is brief. This is the only honest way to fulfill the promise of every potentially habitable planet, without pretending that every world is equally known. Some destinations receive a detailed case because observations already exist. Others appear as members of a controlled group whose value will emerge from comparison. None is silently promoted from candidate to habitat. The atlas now answers where we should look, but it still cannot answer what we will find. Orbit, size, mass, stellar energy, contrast, and geometry determine opportunity. Habitability requires atmosphere, climate, water, chemistry, and time to converge. The final stage of our journey must therefore define what evidence would transform one of these catalog entries from a promising target into a genuinely habitable world. To transform a catalog entry into a habitable world, astronomy needs more than one spectacular signal. It needs several independent lines of evidence that describe the same environment. The passport introduced at the beginning of our journey must be completed as a connected case: a suitable orbit, a rocky body, a surviving atmosphere, temperatures compatible with liquid water, accessible chemistry, and stability across meaningful time. The first stamps are already available for many candidates. Repeated transits or radial velocity measurements establish an orbit. Stellar observations estimate the energy reaching the planet. Radius and mass can support a rocky interpretation. But these are conditions around habitability, not direct evidence of a habitable surface. The decisive transition begins when telescopes constrain the atmosphere. An atmospheric detection would answer the most immediate uncertainty: whether gases surround the world at all. Their pressure and composition would determine how effectively heat moves, whether greenhouse warming is moderate or extreme, and whether surface water could remain stable. Carbon dioxide might provide necessary warmth near an outer edge, or contribute to dangerous heating near an inner one. Water vapor could indicate an active reservoir, while still leaving its location and quantity uncertain. Temperature must then agree with the atmospheric interpretation. Thermal emission can constrain the heat leaving a planet. Phase measurements may show whether energy moves from day to night. A world with a substantial atmosphere should behave differently from a bare rock under many conditions. Yet clouds, surfaces, and atmospheric chemistry can overlap, so one temperature or wavelength cannot settle the climate. Convergence matters again. Evidence of water would require equally careful language. Water vapor in an atmosphere does not automatically reveal an ocean. A surface temperature compatible with liquid water does not prove that water is present. A low density might suggest a water-rich interior without showing exposed seas. The strongest case would combine atmospheric water-related signals, climate constraints, bulk composition, and models that remain consistent across observations. Long-term plausibility forms another part of the case. The host star's age and radiation history must allow the atmosphere and water to survive or be replenished. The planet's gravity and interior must support the inferred gases. Geological activity may recycle material, though the details may remain inaccessible. A snapshot of clement conditions becomes more meaningful when it fits an evolutionary history, rather than requiring an unexplained coincidence. Only after this environmental case is established does the search for life become scientifically interpretable. Some gases can be produced by biology on Earth, but they can also arise through non-living chemistry under other conditions. Oxygen is a central example. Photosynthesis supplies much of Earth's atmospheric oxygen, yet water loss and other processes can create oxygen without life. Detecting oxygen alone would be important, not decisive. The same caution applies to methane. On Earth, organisms produce substantial methane, but geological reactions can also generate it. A combination of gases maintained far from chemical equilibrium may be more suggestive than one molecule. Oxygen and methane together, for example, would demand explanation because they react and require sources to remain abundant. Even then, the star's ultraviolet spectrum, the planet's geology, and atmospheric chemistry must be examined for false positives. A biosignature is therefore not a magic word hidden in a spectrum. It is a pattern whose most convincing explanation may be biological, after plausible non-biological pathways have been tested. The claim grows stronger when several molecules, surface or seasonal behavior, and environmental conditions converge. It weakens when the planet lacks stable liquid water, or when the host star drives chemistry that imitates life. Current instruments are beginning this work, but were not designed to complete every stamp for an Earth analog. Webb can test atmospheres around favorable small planets, especially those transiting small stars. Its measurements of TRAPPIST-1b and c demonstrate the power of ruling out thick atmospheric scenarios. Continued observations of temperate worlds can narrow possibilities further, though signals remain small and stellar contamination remains challenging. Extremely large ground-based telescopes will add collecting area and high-resolution spectroscopy. By separating fine spectral features and using Earth's motion relative to distant systems, they may test atmospheric molecules in favorable nearby planets. Their observations can complement space telescopes rather than replace them. Each platform operates through different wavelengths, atmospheric interference, contrast limits, and target geometries. The Habitable Worlds Observatory represents a more direct ambition. NASA describes it as a future large optical, ultraviolet, and infrared space telescope, designed specifically to identify potentially habitable planets around other stars. Its main objective is to directly image at least 25 such worlds and use spectroscopy to search their atmospheres for chemical evidence, including gases such as oxygen and methane. That objective is not an achieved result or a guaranteed discovery of life. The observatory remains a developing mission concept, whose final architecture and capabilities require further work. Its importance lies in how the scientific question shapes the instrument. Suppress the glare of nearby stars, isolate faint planetary light, measure spectra, and build a comparative sample rather than depend on one extraordinary world. Directly imaged planets around nearby sun-like stars could correct one of today's largest biases. Current rocky atmospheric targets cluster around red dwarfs because transits are stronger and more frequent. A future observatory designed for reflected light could investigate wider orbits around quieter, more sun-like stars. The atlas would expand into territory that Kepler suggested but could not characterize. The intellectual climax of the journey is therefore not a single best planet. It is an explanatory system. Orbital surveys identify where liquid water climates are physically possible. Mass and radius test whether the body is likely rocky. Stellar observations reconstruct environmental pressure. Spectroscopy detects or excludes atmospheres. Thermal measurements test heat transport. Chemistry searches for water and disequilibrium. Time connects all these measurements into an evolutionary history. When those threads agree, a candidate can move beyond a green band. We might identify a rocky planet receiving suitable energy, retaining an atmosphere with moderate greenhouse gases, redistributing heat, and showing water-related signatures. That would provide the first strong evidence of a potentially habitable environment beyond the solar system. Biosignatures would then become the next question, not a shortcut around the environmental work. But the rulebook now encounters its major exception. The entire exoplanet atlas has been built around surface liquid water, heated mainly by a star. Our own solar system contains worlds that challenge that restriction. Europa and Enceladus orbit far outside the Sun's classical habitable zone. Yet strong evidence indicates that both contain liquid water oceans beneath ice. Europa's surface is frozen, but multiple lines of evidence support a salty ocean below its crust. Internal heat and tidal flexing from Jupiter's gravity help keep water liquid. The ice blocks easy observation and separates the ocean from sunlight, but it does not eliminate chemistry or energy. A surface-based habitable zone search would classify Europa's orbit as far too cold, while missing the environment hidden underneath. Enceladus makes the exception even more direct. Saturn's small moon releases plumes from fractures near its south pole. Cassini flew through material connected to the subsurface ocean, allowing instruments to sample particles and gas without drilling through the ice. The mission found water, salts, organic compounds, and molecular hydrogen. The hydrogen supports an interpretation involving reactions between liquid water and warm rock, potentially including hydrothermal processes. These findings do not prove that Enceladus contains life. They establish a far more disciplined claim. The Moon possesses liquid water, useful chemistry, and a source of chemical energy that could support metabolism if life exists. In passport terms, Enceladus earns stamps through an entirely different route. Starlight does not maintain an exposed ocean. Tidal and internal energy sustain a buried one. The ocean worlds do not make the classical habitable zone obsolete. Surface atmospheres can be examined remotely, while oceans beneath kilometers of ice are far harder to detect around exoplanets. The zone remains a practical way to select worlds whose water and atmospheric chemistry might influence observable light. Its limitation is ontological. not operational. It maps one important kind of habitat. Not every environment nature can create. This complication expands the title. A journey through every potentially habitable planet cannot literally contain every potentially habitable place. Moons may host oceans. Rogue planets could retain internal heat. Buried environments may exist where no surface spectrum reveals them. Our present catalog is shaped not only by what habitability may be, but by what astronomy can detect across light years. The achievement remains profound. 30 years ago, there was no population of rocky habitable zone exoplanets to rank. Today, dozens can test climate boundaries, atmospheric survival, stellar influence, and observational methods. Webb is constraining real rocky worlds. Future telescopes are being shaped around the goal of directly examining nearby candidates. The search has moved from imagined destinations to falsifiable environmental cases. The strongest answer to our governing question is now available. A potentially habitable planet is a target whose measured properties allow a habitable environment under explicit assumptions. A genuinely habitable world will require converging evidence that those conditions actually exist. An inhabited world will require an additional, harder case in which biological explanations survive every serious alternative. Earth remains the only world where all three levels are confirmed. The 45 catalog planets occupy earlier positions on the path. Some possess only orbit and size. A few offer mass, density, or atmospheric constraints. None yet supplies the complete environmental chain. The ocean moons remind us that even a completed surface water atlas would not contain nature's entire answer. Our map preserves both truths. Many decisive tests are possible, yet no passport beyond Earth is complete. The journey can end without exaggeration or disappointment. We began with an atlas that could not honestly be drawn. More than 6,000 confirmed exoplanets filled the galaxy with destinations, yet Earth remained the only world known to hold surface oceans, a stable atmosphere, active chemistry, and life. The distance between those two facts created our journey. As of the published 2026 catalog used here, 45 known planets satisfy a stated combination of rocky size or mass and position within an empirical habitable zone. 24 also fall within a narrower zone informed by three-dimensional climate modeling. These are the numbers behind the title, but their meaning is conditional. They identify places where surface liquid water may be physically possible under suitable conditions. They do not identify 45 habitable worlds. Some candidates carry stronger passports than others. TRAPPIST-1, D, E, F, and G, and LHS 1140b have both mass and radius measurements. Proxima Centauri b is extraordinarily close and receives roughly Earth-like stellar energy, but its radius and atmosphere remain unknown. 2I 700, GJ 1002, Wolf 1069, and the distant Kepler systems test different stars, climate boundaries, and observing methods. Every candidate contributes a question, even when it cannot yet supply an environmental answer. The journey also revealed why no planet can be judged by one green ring. Venus receives abundant sunlight, but is trapped beneath a crushing greenhouse atmosphere. Mars records ancient rivers, while its modern surface remains cold and dry. Around red dwarfs, close temperate orbits improve detection, while stellar activity may threaten atmospheric survival. Size, orbit, and energy open the investigation. Atmosphere, water, chemistry, geology, and time determine where it leads. Observations have begun closing possibilities. Webb has shown that TRAPPIST-1b lacks a significant heat-moving atmosphere under the measured conditions, and that TRAPPIST-1c is unlikely to possess a thick Venus-like carbon dioxide atmosphere. These are not failures of the search. They are examples of the atlas becoming empirical. A world becomes more real each time evidence replaces an unrestricted scenario. The next steps are clear. Better stellar measurements will move uncertain planets into or out of catalogs. Repeated spectra will test atmospheres around favorable transiting worlds. Extremely large ground telescopes will add high-resolution observations. A future Habitable Worlds Observatory is intended to directly image a sample of potentially habitable planets and search their reflected light for atmospheric chemistry. None guarantees life, but each is designed to complete another passport page. Even that program will not map every possible habitat. Europa and Enceladus contain oceans beneath ice, far outside the classical surface water zone. Their internal and tidal energy shows that nature can create habitable possibilities, where starlight alone would predict frozen surfaces. Buried oceans around distant planets or moons may remain invisible to methods built for atmospheres. So the direct answer is both larger and smaller than the title suggests. We can journey through every member of a defined, date-stamped catalog. We cannot journey through every potentially habitable world that exists, because many remain undiscovered, misclassified, or hidden from the measurements available today. And among the worlds we know, only Earth is confirmed habitable. That conclusion does not return us to ignorance. Astronomy has moved from asking whether planets exist beyond the Sun to identifying which rocky worlds can test water loss boundaries, greenhouse limits, atmospheric survival, and biosignature methods. The map remains incomplete because each border and blank page now represents a measurement that can be made. Earth still holds the only completed passport. Around other stars, dozens of pages have received their first stamps. The real journey is no longer toward imagined blue planets. It is from possibility to evidence, one world at a time.